Okay, hello, welcome to my channel. My name is Anch, and in this video we're going to go through some examples, all right, of proofs by mathematical induction. Okay, so we'll just get right into it. So please, if you like this video, please don't forget to subscribe to my channel, and if you have, thank you so much. Share it with your friends, and of course, let's just get right into it, all right? If you have any question, put in the comment section below. After everything, I'm going to answer, and you can see some so after some while. Okay, so we have for all n greater than or equal to 1. This is another way of saying that is for all positive integers n. All right, let's put it this way, that this n represents an integer greater than or equal to 1. So that's another way of saying for every natural number. We want to show that this sum on the left hand side, that is 1 over 1 times plus 1 over 2 times 3 plus 1 over 3 times 4 plus, and so on and so forth, till we get to 1 over n times n plus 1. So when you multiply a number with the next number, okay, that is from 1, 2, and so on. When you multiply each of those whole numbers, positive whole numbers, with the next one, the result, and you add them together, the result can be of this form. Okay, so we notice that the product is in the denominator, the numerator stays as 1 throughout. Okay, great. So to show that this is true, you're going to be using the principle of mathematical induction, of course. So we just start off with the proof. So let me just use black for that. So we're going to say, okay, so we're going to say proof. I'll be doing this by the principle of mathematical induction. Good. So as always, we're going to start off with the base case. Okay, that's the first case. We're going to say the base case. In this case, we are here, this step, we are going to be using the first element in this set. This is a set of integers greater than or equal to 1. In other words, the first element there is 1. So you want to check when the number of such fractions is 1, okay, and we add 1. Well, when the number of such fraction is 1, well, will it be the same thing when we substitute n equals to 1? So for the base case, we check when the number is 1, that is when n is 1. Okay, so what we have to do is to check the left hand side for 1, that is for the first fraction, for the first of this kind of fraction, and then we compare it when n is 1 on the right hand side to see what we get. All right, so we notice that on the left hand side we're going to have 1 divided by, well, 1 times 2 of course is 2. On the right hand side we're going to substitute 1 for n, so you say 1 divided by, now in place of n we're going to put in 1. That's what we've done here. Let me do this. Then we add this 1 to that. Of course, this is 1 divided by 1 plus 1, which is 2. So the first case there is the same thing when n is 1 on the right hand side. So that means that the base case is true. So you can say it's true. Okay, great. Now, usually I like to give this kind of statement a name. Okay, so if I call it, let's call it P of n. What I want to do here is that I'm just calling this maybe a propositional function, or just some propositional, some proposition that we need to check if it is either true or false. All right, so we need to check if it is valid. Good, so we just give it a name to help us. Anyway, that's for the base case. You can even go ahead to check for the second element of the set, which is going to be 2. That is when n is 2. So that means when you add the first two terms together, so this is the first term, this is the second term, when you add the first two terms together, will it give you the same thing when n is 2 on this right hand side? Okay, something like that. Of course, that so you just check. Of course, it's going to be true, because this is 6, so 1 over 6, this is 1 over 2. Well, multiply 2 on bottom by 3, that'll be 3. 1 over 2 is the same thing as 3 over 6 plus 1 over 6, that is 4 over 6, which is the same thing as 2 over 3. So when n is 2, you're going to have 2 over 3. That works, right? Good. Okay, so the next, in this next step, we usually say assumption, then induction. Of course, we can join the two together. We can just call it the induction step. So what we'll be doing here is to assume that this statement is true for some arbitrary positive integer k. So we assume, of course, we gave the statement a name. Assume that P of n is true for n equals to k, where k is some positive integer. Good. That is, we assume that this statement here, which we've labeled as P of n here is true when n is k. That is, when the number of terms we are adding is actually k, right? This is like adding n terms. So when the number of terms you are adding is k. Good. And in this case, k is also positive, that is greater than or equal to 1, and it's an integer. I'm just showing you here that is a whole number, of course, but that's the same thing we said for the n. So for what does that mean for this statement to be true for that? That means that when we want to add the number of terms, there are going to be k of them. So we will not get up to n. Okay. Of course, these are just arbitrary, so it doesn't really matter. Okay, so with that is going to be 1 over 2. Oh, sorry, 1 over 1 times 2, which is just 1 over 2 anyway. But let's just put it in the form, right? 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5, and so on and so forth, till we get to 1 over, of course, we said k, right? 1 over k, okay. We add 1 to that, so k. That is when n is k. That's what we're going to get. And by assumption, we are going to assume that this statement is true, which means that when we add the first k of such terms together, we're going to get k divided by k plus 1. So it is true for k. Oh my god. Let me clean it and write it again. Okay, that's nice, isn't it? Alright, great. So that's the assumption, that's what we are assuming. So I'm going to give this a name. We can call this equation 1. Good. So for the induction step, we assume that this statement is true for some k, and then we are going to check whether the statement is true for the successor of k, that is for k plus 1. Good. So the mathematical induction works this way. To check if the statement is true, we can easily just think about it this way. We can say, let's substitute n equals to 1, that is the first term, and check if it will be the same thing as when the number of terms is 1, that is when n is 1. Let's add the first two terms together and say when the number of terms we are adding together is 2, that is when n is 2. Are they the same? Substitute for 3, substitute for 4, for 5, and so on and so forth. But we can't keep doing that for each natural number or for each positive integer. Alright? So in that case, we know what we want. Like after 1, 2, after 2, 3, after 3, 4, which is 3 plus 1, after 4, 4 plus 1, after 5, 5 plus 1, so on and so forth. So we just choose an arbitrary natural number k, and then when we assume that it's true for that arbitrary natural number, whether k can be even 99, and then we now check whether it's true for the next one. Right? If that is true, it means that it will always be true for every positive integer, because we just showed for an arbitrary one, so it's true for each positive integer, right? So that's what we're going to be doing. So the next thing is we now check whether the statement P of n is also true when n is k plus 1. That is when the n becomes the successor of k. Good. So the successor of a number is the next number. Alright? The successor of a whole number is the next whole number. Good. So we check whether this is true for n plus 1. That is, we want to check if when we add the first k plus 1 terms, okay, whether we are going to get k plus 1 divided by k plus 1 plus 1. Okay, so let's see. Well, we'll be making use of this given that this is true, right? We want to check if this is true. So adding the first k plus 1 terms, we are going to have 1 divided by 1 times 2 plus 1 divided by 2 times 3 plus, and so on and so forth, up to k plus 1 of them, right? But before k plus 1, which is a term, after kth term, we're going to have k, the kth term first, which is this, right? So we have 1 over k into k plus 1. Good. So we reach this term first before the k plus 1 term. So we can write the k plus 1 term this way. Take note that in place of n, we're going to put in k plus 1, right? So you keep that in mind. So that's going to be k plus 1. Then we now open this up. We now add we now put in k plus 1 for n here, this inner n. That will be k plus 1 plus 1. So that's going to be k plus 2. Right? Okay. So we have that. I hope it's clear enough. Let me write it again. Good. Okay, so now we're going to use the fact that we're going to use the assumption we made anyway. Now this is what we do. We'll see that from here to here, that is, the sum of the first k terms was already given by equation 1 to be k over k plus 1. So we're going to replace it. Divided, say, k divided by k plus 1 in place of the sum of the first k terms. Then we are going to add this to that. That will be 1 divided by k plus 1 times k plus 2. Okay, great. Now, let's add these two fractions and see what we have. Well, this equality is from equation 1, right? So you can say from equation 1. So, yeah. To add these two fractions, we just have to get a common denominator. And we can do that simply by multiplying this numerator and denominator by something. So you multiply the numerator by k plus 2. Alright? Multiply the denominator by k plus 2. Just to make sure that the denominators are the same. But what we've done here is multiplication by 1, right? In that case, we're going to have k times k plus 2 at the top. In this case, the denominators are the same, so we can keep a single denominator and then add the numerators. So that's going to be k plus 1 times k plus 2. So we add the numerators. This is just plus 1, right? Good. So let's multiply the numerator and see what we have. What is going to be k squared plus 2k plus 1. K squared plus 2k plus 1. When we expand a squared term, it's always maybe a plus b. A squared plus 2ab plus b squared. So this looks like when you multiply out the numerator, that is k squared plus 2k plus 1, right? That has, this is a expansion of k plus 1 squared. So this is going to be k plus 1, k plus 2. So of course this is going to be k plus 1 squared, which one of them can cancel out with the k plus 1 at the bottom, and we are left with this, right? This is k plus 1, that is, this numerator here is k plus 1 times k plus 1, which is k plus 1 squared. And one of this k plus 1 will cancel out with this other k plus 1, right? We're left with k plus 1 at the top, only one left, and then divided by k plus 2 at the bottom. And this is exactly what we want to show, that k plus, the statement is true for k plus 1. Look at it. K plus 1 divided by k plus 1 plus 1, that is k plus 2. And we've shown that. So we can conclude by principle of mathematical induction that since the statement is true for the base case, that is for when n is 1, and whenever it's true for an arbitrary k, it is true for its successor, okay, we can conclude that the statement is true for all positive integer n, that is for all n greater than or equal to 1. Okay, great. So I don't have enough room to go through all of that, but that's what you basically say. Okay, here is the second example. Here we want to show whether this statement is true. That is, whether the sum of squares can be written as n into n plus 1 times 2n plus 1 divided by 6, where the n is the number of squares we are adding. Alright, so if we add two squares together, that is 1 square plus 2 square, that's the first two squares, that's going to be 5. It will be the same thing when you substitute 2 for n here. Let's just look at it. 2 into 3, okay, that's 5 here. So we say 3 times 5, 15 plus 2, that's this is it, 2 here. Alright, 2 into 3, that's 6. You now multiply 6 by 5, that is going to be 30. Okay, that's a 30 divided by 6, that's 5. 5 is the same thing as 1 squared plus 2 squared, as we're talking about. Okay, so we've just done a verification, but let's just start off as usual using the principle of mathematical induction. So let's just say proof here by BMI. Okay, so the first of which is always in the verification case. Okay, so we're gonna say the base case, and what we'll be doing here is to check for n being 1. So when we are adding, or when we're just picking the first term, actually you can actually add one term together. It doesn't make sense, right? Good. So for that is the base case, that's the verification when the number of terms is 1. So when the number of terms we are adding is 1, that is when we're just picking the first term. Okay, this is what we have. On the left hand side, we're just going to have 1 squared, we check if it's the same thing as this. So on the right hand side, in place of n, we're going to put it in 1, right? So we have 1 plus 1. Okay, so in this case we have 2n, that is 2 times 1. Okay, we're going to add 1 to that. Then we divide it by 6. So this is 1 times, of course, we just ignore it, right? 1 plus 1 is 2. 2 times 1 is 2 plus 1, that's 3. So 3 is here, 2 is here, that's 6. 6 divided by 6 is the same thing as 1, which is the same thing as 1 square. So 1 square is the same thing as 6 divided by 6, which is 1. So that holds, alright? So this is true. So you say P of n is true when the number of terms is 1. Good. That's the base case. The next thing is to go to the induction. Okay, we can just go to the induction straight up without writing assumption. So we are going to say that that is a induction. Let's forget about the assumption. So here we are going to assume that this is true for some arbitrary natural number. Okay, so you notice that we've already done for 1 and we did for 2 earlier in our head. So we've shown that this is true for the first 2 elements in this set natural number system. Okay. Okay, so in that case, we can not just keep doing for 3, for 4, that is when the number of terms is 3, when the number of terms is 4, to know if this sum you hold on both sides. Okay, so because of that, we're going to assume that it's true for some arbitrary number of elements, and then we're going to show that it's true for the next one. So assume that the statement P of n is true when the number of elements is some k. That is, we'll assume that means we're going to assume that when we add the first k squares together, that the result will stay this way, where n will be replaced by k. Right? That's the way the number of terms will be k. So we're going to have 1 squared plus 2 squared plus and so on and so forth up to k squared. Okay, coming up to k squared. I don't like the way that k is written. 1 squared plus 2 squared plus 3 squared up to k squared is going to be, well, we're going to replace each of these n's by k. That is going to be k into k plus 1 into 2k plus 1 divided by 6. So each of these will just be k, right? Good. That's the assumption. So we can give this a name. We can call it equation 1, as always. Good. The next thing is to use the fact that this is true. That is, we say that assuming that P of n is true when n is k, we want to show whether P of n is true when n is the successor of k. So we check whether, alright, or we show whether the statement P of n is true when n is the successor of k. Okay, so what does that mean? That means that when we add the first k plus 1 squares together, are we going to get something of this form where each of these n's will be replaced by k plus 1? If that is true, then we've shown by mathematical induction that the statement is true for all natural number n. For every natural number. Okay, so let's see what we have. So we're going to add the first k plus 1 squares together. 1 squared plus 2 squared plus and so on and so forth plus now k plus 1 squared, right? But you notice that before we reach k plus 1, we already have k somewhere just before k plus 1. So I'm going to put it plus k squared, then plus the next number squared, which is going to be plus k plus 1 squared, right? Which is the number after k plus 1 squared. All right. Yeah. Now you notice that from the whole of this, we can use equation 1 to replace the whole of that, right? So here we'll just be checking whether the left hand side will be the same thing as the right hand side, given that n is when n becomes k plus 1. So from equation 1, we can make a substitution for the first term of the first k squares. We can call it k into k plus 1, right? So you notice the left hand side is the same, so we're going to equate it to the right hand side. That's 2k plus 1, okay? We divide it by 6. That's for this part. Then we are going to add k plus 1 squared to that. Good. Now, the next thing will be to try to simplify this till we get something of this form, where each of these will be replaced by k plus 1. In other words, we're going to get k plus 1 here, k plus 1 here, then 2 into k plus 1 plus 1. So how can we get that out? Well, let's see. To add these two fractions, we can just multiply this by 6 and then divide by the 6. So in other words, the denominators are the same, so we can add the numerators by keeping a single denominator. So we're going to keep 6. And then we're going to add the numerators. But remember, take note that k plus 1 is common, so we can factor out k plus 1. When we factor out k plus 1, no k plus 1 is here. It's over here again. So we're going to have k into 2k plus 1, alright? Here k plus 1 is out, so we're left with 6 into k plus 1. Since there were square of k plus 1, so one of them is out, okay? Yeah. Now, let's see. We have this, maybe we just have to expand and then factorize again, okay? Yeah, so let's have k plus 1 here, yeah, then into, well, here we're going to have k plus 2 somehow. So let's open up this bracket. So that means we're going to have 2k squared. Let's make this 6 become a little bit smaller. 2k squared plus k plus 6k, that is plus 7k. Okay, then we're going to have plus 6 divided by 6. That is by expanding, all right, and adding the two brackets. So we have k plus 1 out here. Now, inside here, let's factorize this term. Notice that this is a quadratic. So to factorize a quadratic, where the coefficient of the k squared term is 2, right? So we just multiply 2 by 6. That will give us 12. We now think about two factors, which when we multiply, we get 12, and when we add, we get 7. Okay, so which two factors? That's 4 and 3. Okay, 4 and 3, 4 plus 3, 4 times 3 is 12, while 4 plus 3 is 7. So we can write this thing, the thing this way. That would be 2k squared, right? We're going to add 4k. We're going to add 3k. Maybe we should, let's grab and factorize. So we're going to add 3k, and then we are going to add 6 to that. Good. So that's by writing the quadratic expression at the top. Alright, so let's see what we have. Well, this is just k plus 1 here. Now, we factor out 2k from the first term. So we factor out 2k from this first two, alright? So we're going to have k remaining here, and then only 2 remaining here. That was going to be k plus 2. Similarly, we're going to factor out a 3 from here. So we factor out a 3, that's positive 3. We'll be left with k plus 2 as well. Good. So the denominator still stays at 6. Okay, so that means I'll need a little room here to finish this off. So let's clean off the base case. Now, you notice that at the top there, we can write it as, this is not where we're starting. Okay, so that's k plus 1. Now, we notice that k plus 2 is common in this second bracket, right? So we can factor out a single k plus 2. We factor it out, k plus 2. We'll be left with 2k plus 3, right? That's going to be 2k plus 3 divided by 6. Now, let's see. Keep in mind what we wanted. We wanted something of this form, where each of these ends will be replaced by k. That is k plus 1 into k plus 1 plus 1. Well, k plus 1 plus 1 is k plus 2. This is k plus 1. This is k plus 2. That means if this part gives us k plus 2k plus 3, we are done, right? And it is. Look at this. This is k plus 1, which we have already. This is k plus 2. We can write this such that we have 1 added outside, right? This is what we're going to do. Now we're going to write this term as 2k 3 can be written as 2 plus 1 plus 2 plus 1. Grouping these two terms together, we factor out the 2. 2 into k plus 1. Then we now add this 1 to that. So you see, 2 into k plus 1 plus 1. Good. So that's what we wanted. So you're going to say 2 into k plus 1, right? Then we add 1 to that. So you notice that this other one can be written as k plus 1. Then you add 1 to it. This one is already k plus 1. Okay, so yeah, that's it. So let's just clean it up and write the denominator anyway. So we've shown that by principle of mathematical induction that statement p of n is true for all natural number. That is for every natural number. How do you do it? Check for the best case. Okay, assume that it's true for some arbitrary number of terms you squared, that's number of squares, and then use the fact that this is true, use this assumption to show that it's true for the next one. So we used the assumption here by replacing this thing with equation 1, and then we've shown that this statement is true for k plus 1, that is when n is k plus 1. In that case, by principle of mathematical induction, we've shown that the statement is true for all n. So we can say n of proof by doing this. Alright? Okay, great. So let's do just one more example. Okay, we have a third example. Here we want to show whether this statement s of n, which tells us that n to the third power plus 2n is always divisible by 3, is true for all natural number n. Good. So what this means is, when you have a natural number, you raise it to power 3, you add it with 2 times that number. We want to check if this is always divisible by 3. In other words, if that will always be a multiple of 3. Alright? So a number is said to be a multiple of 3 if 3 is a factor of that number. That is, if 3 divides that number without any remainder. Okay? So this is it. If we say a number a is divisible by m, that is, it will mean m divides a, that tells us that there is a certain integer, okay, maybe let's call it L. There's a certain whole number L, such that when we multiply m with that whole number, we are going to get a. That's what it means for m to divide a, or a to be divisible by m. Okay, so that means if we compute a over m, the result will be a whole number. Now in that case, we say m divides a, or a is divisible by m. So this is divisible by 3 means that if we divide this by 3, the result will just be a whole number. There will be no remainder. Okay, that's what we want to check. Alright, so let's see. You are going to be using the principle of mathematical induction, of course, to prove this. So we start off with the proof, and it's going to be by the principle of mathematical induction. Good. So what do we do first? Of course, as usual, we're going to start off with the base case. That is for the first element in this set. Okay, don't get it wrong. We know most of the examples we've done, the first element will always be here. But sometimes I can give you where the n is a positive integer greater than or equal to 3. So you need to know greater than or equal to 3. So the first element here there is going to be 3. Alright? When I say positive integer greater than 3, that means the first element there will be 4. So you're going to use 4 in that case. Well, here, instead of natural numbers, you're going to start with 1. Right? Okay, so if you don't believe that the 1 is the first natural number, maybe you can think about the question as n is a positive integer, that is, integers greater than or equal to 1. Alright, great. So let's see what we have. So for the base case, okay, for the base case, what do? We check when n is 1. We want to check if this will be true, that is, will this number be divisible by 3 when n is 1? Okay, so in other words, we're gonna take the cube of 1. Oh, sorry. We're gonna take the cube of 1, alright? We are going to add it with 2 times 1. This is what this gives us. 1 to the third power is 1. Plus 2 times 1 is 2. So 1 plus 2 is 3. Is 3 divisible by 3? Of course it's true. Every number is a factor of itself. So that means this is 3, and 3 is divisible by 3, so that statement is true from here. So we can say S of n is true, considering the base case. That's the verification step. Alright, let's go to the second step, that's the induction. We're going to assume and then check. So we do an induction. Good. So we assume that for some arbitrary n, that this statement S of n is true. Assume that S of k is true for some arbitrary k. So as you see, I said assume that S of k is true. The same thing as saying assume that S of n is true when n is k. Alright, so when n is k, we can easily put k here. That's what we're saying. Okay, that is what that means is that when we substitute k for n, the result will always be divisible by 3. That means that 3 will divide any expression that has k in place of n. Alright, so you're going to have the cube of k plus 2 times k. Good, that's what it means. And from what we just explained at the beginning over here, it means that there is a whole number such that when we multiply that whole number by the denominator here, which is 3, that's the divisor, the result will give us k cubed plus 2k. If 3 divides k cubed plus 2k, the remainder after dividing this number by 3 will be 0. In other words, the division will give us a whole number. So what that means is that that implies that there is an integer, let's call it L, such that when we multiply that integer L by 3, the result is going to give us k cubed plus 2k. Good. That is the assumption. So we can call this equation 1. And then we're going to use this assumption to check whether this statement is true for the successor of k, that is for the next natural number. So when n is k plus 1, what happens? Alright, we want to check whether when we substitute k plus 1 in place of n, whether this will be divisible by 3. Okay, so we want to check. We want to show whether, alright, we want to show whether 3 will divide this expression where each of those n's will be replaced by k plus 1. Alright, so you put k plus 1 here, then you put k plus 1 here. That's what we want to check. In other words, we want to check if there exists a natural number. No, if there exists an integer such that when we multiply that integer by 3, we're going to get this expression. That is to show if there is an integer, let's call it j. Alright, let's call that integer j, such that when we multiply that j by 3, so such that 3j is the same thing as k plus 1 to the third power plus 2 into k plus 1. In other words, if we can rewrite this thing here, this k plus 1 to the third power plus 2 into k plus 1 as a multiple of 3, it means 3 will divide it. Alright, that's what we mean. This means a multiple of 3, 3 times some whole number, where this whole number can be maybe a combination of other whole numbers, like the addition of other whole numbers and the rest. Anyway, you will see. So that's what we want to do. That's just the outline. Alright, so let's see what we have. Of course, we always make use of the assumption, which we've tagged equation 1 here. Let's expand this k, this right hand side, and see what we have. But k plus 1 to the third power plus 2 into k plus 1 is the same thing as what? When we expand this k plus 1 to the third power, of course, using binomial theorem of expansion for the third power, you're going to have 3k squared plus 3k plus 1. Alright, we add it with, while we open up these brackets, we're going to have 2k plus 2. Good. Now this how I'm going to write this. I'm going to be writing this paying attention to my equation 1. I want to get something of this form, k cubed plus 2k. plus 2k. Okay. Yeah. All right. So let's see. This is supposed to be, okay. So this is going to be k cubed. I've seen k cubed plus 2k here. All right. So I'm going to try to write this so that we have that out first. Plus 2k. So this k cubed plus 2k. I'm picking these two first. Then I'm going to add 3k squared plus 3k plus, well, 1 plus 2 is 3. Good. So this is, well, you notice that from equation 1, k cubed plus 2k was given to be 3l. So we always make use of the assumption to check, to show that the successor case of the successor will be true. So from equation 1, we're going to put in 3l in place of k cubed plus 2k. So we're going to put in 3l, all right? Then we add it with the remaining part, which is 3k squared plus 3k plus 3. Of course, you've seen it. Now, look at this. 3l plus 3k squared plus 3k plus 3. These are what? Each of these are multiples of 3. So the sum of multiples of 3 will be a multiple of 3. That means we can factor out the 3. When we factor it out, we're going to be having l here plus k squared plus k plus 3. Good. Now, what does this mean? This is a 3 outside multiplying something. What is this? L here, we said L should be an integer. Okay? We know that k already is a natural number, which is a whole number. So L is also a whole number, but in a more general case anyway. This is a whole number. The square of a natural number will be a natural number. Plus, the sum of two natural numbers will be a natural number. This is 3 already. No, that's not supposed to be 3. Sorry, it's 1. Sorry about that. You know, when you factor out 3, you'll be left with 1 here, right? So this here, inside this bracket, we have sum of whole numbers, which will again be a whole number. That means that we have rewritten this thing as 3 times some whole number. In other words, this guy here is a multiple of 3. So what does that mean? That means that 3 divides this k plus 1 to the third power plus 2k plus 1. Assuming that 3 divides this part. So this is enough to show us that by principle of mathematical induction, this here is always divisible by 3. That is to say, this statement is true for all natural number n. Good. Okay. Anyway, that's a nice place to stop. Okay, I need to make a pen. If you have a question, please do what to put in the comment section below, and I can come up with something else to answer you. Right. Thanks for watching. Please share this video with your friends, and I'll see you in our next video.